Hello everyone, welcome to the exercises for DGD 4, and we're starting with some more examples of induction, now using exponents. So 4.1.2 part 1 is to prove that for all k, the expression 5 to the power of 2k minus 1 is divisible by 24. So proof, we'll be doing this by induction, which means we need a base case. Since we're inducting over the natural numbers, our base case is k equals 1. And then we're just considering the expression 5 squared minus 1, which is 24, which is divisible by 24. So the base case holds. Now for our inductive step, to make sure we get the correct inductive assumption, so let k be greater than or equal to the base case, and assume that the condition holds at k, which is that 24 divides the expression 5 times 2k minus 1. This is the same as saying that there is an integer j, such that 5 to the 2k minus 1 is equal to 24j. And now we would like to consider the next expression, which is 5 to the power of 2k plus 1 minus 1. We can expand this, looking to isolate 5 to the 2k. So this is 5 to the 2k plus 2 minus 1. And this is 5 squared times 5 to the 2k minus 1. So we have this coefficient of 25. What we can do is use this inductive assumption and rearrange it to isolate for 5 to the 2k. So this is the same as saying 5 to the power of 2k is 24 times j plus 1. So we can say that this is 5 squared times 24j plus 1 using our inductive assumption. Now this we can just expand. This is 25 times 24j plus 25 minus 1, which is 24 times 25j, just swapping the 24 and 25, plus 24. And now 24 factors out nicely. We get that this is 24 times 25j plus 1, which is a multiple of 24. This means 24 divides this expression, which is the expression at k plus 1. So the inductive step holds, which means that we've completed the proof by induction. Part 2 is a similar exercise. We're to show that for all natural numbers k, the expression 2 to the exponent of 2k plus 1 is divisible by 3. So our proof will be by induction. Since it's by induction, we will consider a base case of k equals 1, since we're inducting over the naturals. In this case, we're looking at 2 to the power of 3 plus 1. So this is 8 plus 1, which is 9. And 9 is divisible by 3, as it is 3 times 3. So this finishes our base case. For the inductive step, let k be greater than or equal to the base case of 1, and assume that 3 divides this expression at k. And this means that there exists an integer j such that 2 to the 2k plus 1, all plus 1, is 3 times j. So now, as before, we would like to consider the case at k plus 1, which means we're considering 2 times 2 to the k plus 1, all plus 1. And we would like to show that this is divisible by 3. We can expand this somewhat. We'll get 2 to the 2k plus 3 up here, plus 1. And we'd like to find a copy of 2k plus 1. So we can do that by factoring out 2 copies of 2. Like this. And now our assumption here is equivalent to saying that 2 to the 2k plus 1 is 3j minus 1. So we can substitute in 3j minus 1 for this term. This is 4 times 3j minus 1 plus 1, which we can expand. This is 4 times 3j minus 4 plus 1, which is 3 times 4j, swapping the 3 and the 4, minus 3. And now this 3 factors out nicely. This is 3 times 4j minus 1. And so since the expression at k plus 1 is a multiple of 3, this means that 3 divides the expression at k plus 1, which concludes the inductive step. 4.1.4 tasks us with deciding which natural numbers k cause the inequality k squared is strictly less than 2 to the k to hold, and then to prove our claim. So first, we just need to decide which ones of these they actually hold for. We can start by checking 1. 1 squared is 1, and 2 to the 1 is 2. So here it does hold. We can check for 2. 2 squared is 4, and 2 to the 2 is 4. So here it actually fails. It holds on 1, fails, because 4 is equal to 4. It's not strict. So if we look at the next one, 3 squared is 9, and 2 cubed is 8. It also fails here. 4 squared is 16, and 2 to the 4th is 16, so it also fails by being equal here. But 5 squared is 25, and 2 to the 5th is 32, and so here it holds. And at this point, this is only going to be increasing, somewhat slowly. The next one is 36, and then 49, and this is going to be doubling. We're going to get 64, 100, etc., and so this is going to race off. So we expect that it holds for 1 and 5 and greater. So our claim is that k squared is strictly less than 2 to the k for k equal to 1 and k greater than or equal to 5. And now we can prove this by induction. So proof. First we'll do the k equals 1 case. Note, 1 squared is strictly less than 2 to the 1, so k equals 1 holds. Now by induction, we have a base case of k equals 5. Then 5 squared is 25, but 2 to the 5th is 32, and 25 is less than 32. So now for our inductive step, our inductive assumption is to let k be greater than or equal to our inductive base case, which is 5, and to assume that k squared is strictly less than 2 to the k. First, we're going to note some things about k. Since k is greater than or equal to 5, this means that k is strictly greater than 0, which means that k is natural. It also means that k minus 3 is greater than or equal to 2, which is natural. So k minus 3 is natural. And that k minus 1 is natural. Since we have these 3 natural numbers, we can build a new natural number out of them using closure. In particular, I'm going to consider this one. K times k minus 3 plus k minus 1 will be natural. And if we expand this all out, we get that k squared minus 3k plus k minus 1, which is k squared minus 2k minus 1, is natural. This we can expand or change slightly more. We can write this as 2k squared minus k squared minus 2k minus 1, which is natural. And now we have something subtract something else is natural. And so this means that 2k squared is greater than k squared minus plus 2k plus 1. So we have this inequality. Now we'll use our inductive assumption by first considering 2 to the k plus 1. This is 2 times 2 to the k. And by our inductive assumption, 2 to the k is larger than k squared. So this is larger than 2 times k squared. But now we've just shown that 2 times k squared is strictly larger than k squared plus 2k plus 1. And this is equal to k plus 1 squared. So 2 to the k plus 1 is larger than k plus 1 squared, concluding the inductive step. Exercise 4.1.5 tasks us with proving that 2 to the power of n is less than n factorial when n is greater than or equal to 4. And because this is over a range of natural numbers, n greater than or equal to 4, it lends itself well to induction, which is what we'll be using. So our proof is again by induction. But now our base case is 4, since that's the smallest number for which we want this to hold. So our base case of n equals 4. So then 2 to the 4 is 16, and 4 factorial is 4 times 3 times 2 times 1. So this is 6 times 4 is 24. And clearly 16 is less than 24. So it holds in the base case. Now for our inductive step, we want the correct inductive assumption, which is we want to let n be greater than or equal to the base case, which in this exercise was 4. And we assume that the claim holds at n, which is to assume that 2 to the n is less than n factorial. So now we're going to apply this inductive assumption in a chain of inequalities. I'm going to start by just considering n plus 1 factorial. By the definition of factorial, this is n plus 1 times n factorial. And now by our assumption, n factorial is greater than 2 to the n. So I know that this expression is greater than n plus 1 times 2 to the n. But now also, since n is greater than or equal to 4, n plus 1 is greater than or equal to 5, which means it's greater than 2. So this is strictly larger than 2 times 2 to the n, where this step here is since n greater than or equal to 4 means n plus 1 is greater than 5, which is strictly greater than 2. And 2 times 2 to the n is just 2 to the n plus 1. So this implies that n plus 1 factorial is strictly greater than 2 to the n plus 1. So the claim holds at n plus 1, which concludes the inductive step, which concludes the proof by induction. 4.1.7 is another proof of divisibility, which will again use induction. But now instead of being given an expression, we're told that the expression is defined recursively through this sequence. So the first element of this sequence is 10, and to find the next element of the sequence, we use information about the previous one. So to get the n plus first term, we use the nth term, according to this equation. So we will prove inductively that all of these are divisible by 5. So by induction, since we're inducting over all natural numbers, our base case is n equals 1. And then x1 is equal to 10, which is divisible by 5. So the base case holds. For our inductive step, we let n be greater than or equal to 1, and we assume that 5 divides the nth term. Now when we consider the next term, which is x to the n plus 1, we already have a formula for this. This is x to the n squared plus 3xn minus 5, as we were told it is by the recursive definition. But now here we have an assumption about x to the n. In particular, this means that there is some integer j such that x to the n is 5j. Sorry, not x to the n, x sub n. So here we can just replace this. It means that this is 5j squared plus 3 times 5j minus 5. And with a bit of rearranging, we can factor a 5 out of everything here. This is 5 times 5 times j squared plus 5 times 3j minus 5 times 1. So we get the following, which is a multiple of 5, which means that 5 divides the n plus first term, since that's what this expression is. And therefore, the inductive step holds, and we've completed our proof by induction. 4.2.2 is another proof by induction, but now we're employing finite series. So notice that this is an inductive claim for all natural numbers k, where on the left-hand side, k is occurring as one of the upper bounds of summation. And on the right-hand side, it's just a variable. So when we consider the k plus 1 case, it's going to be this that changes, and nothing else in this summation. So this proof by induction proceeds normally. Since it's by induction, we need a base case. And that base case is going to be k equals 1, since we're inducting over the natural numbers. And in this base case, this sum is equal to, because k is 1, just the sum from I equals 1 to 1, which means that there's only one term, which is 3 times 1 minus 2, which is 1. And this expression, where we're allowing ourselves to use rational numbers now and divide by 2, is just equal to 1 times 3 to the 1 minus 1 over 2, which is 1 times 2 over 2, which is 1. So these are equal when k is 1, which is what we wanted from the base case. Our claim is that these are equal, and when k is 1, they are. So now for our inductive step, we're going to let k be greater than or equal to the base case, and we're going to assume the conclusion at k, which is we're just going to assume this entire equality. The sum from 1 to k of 3i minus 2 is this expression here. Now I'm going to consider the k plus 1 case for the sum on the left, which means that this top index becomes k plus 1. And otherwise we're summing up the same terms. So now it's the sum from 1 to k plus 1 of 3i minus 2. A common trick when dealing with inductive proofs over summation is that all we've done here is add an extra term on the end. So this is the first k terms added up, which we express like this, plus the k plus first term that we just added, which is the term where I is equal to k plus 1. Now this summation here, we know what it's equal to. So we can replace it with k times 3k minus 1 over 2 by inductive assumption, and that's being added to 3k plus 3 minus 2. So now we can just go about simplifying this. This is 3k squared minus k over 2 plus 3k plus 1, which is the following 6k plus 2 over 2. And so we get that this is 3k squared plus 5k plus 2 all over 2. Now this doesn't immediately look like the right-hand side at the k plus 1 case, but we can also consider the next version of the right-hand side. And we can just expand this out. So this is k plus 1 times, here we'll get 3k plus 2. And this will give us 3k squared plus 2k plus 3k plus 2 all over 2, which is 3k squared plus 5k plus 2. So here we see that these are equal. So they are equal, which concludes the inductive step. And since we have a base case and an inductive step, that is the proof by induction. 4.3.1 will ultimately end up becoming a proof by induction, but it has a bit of setup. It asks us to consider defining an operation on functions u and v. The operation will be denoted by prime, and it has the properties that u plus v prime, so if we apply it to a sum, is just u prime plus v prime. If we apply it to a product, u times v prime is u times v prime plus u prime times v. And if we have a constant times the function u and we apply prime, this is the constant times u prime. So for a constant c. Now with this prime function defined, we will recursively define a function u in brackets to the k as equal to u to the brackets k minus 1 prime. So really what this means is that it's u with prime applied k times. And u0 is just u because prime has been applied no times. So this is all part of the definition. We have some operation that has these properties on arithmetic, and then we define its repeated application recursively like this with symbols. Now we're asked to prove that if we apply it k times to a product, we get the following formula. The sum from m equals 0 to k of k choose m, these are the binomial coefficients, of u in brackets to the m and v in brackets to the k minus m. So this looks like a binomial formula, but it's for this newly defined operation in terms of prime. And we can prove this inductively. So proof by induction. So we can start with our base case of k equals 1. At k equals 1, uv to the k is uv to the 1, which by its recursive definition is uv to the 0 prime. But anything to the 0 is just itself. So this is uv prime, which we know by the properties of prime is u prime times v plus u times v prime. Okay. Now we can look at the right-hand side, and the sum from m equals 0 to k of all this is Well, we're at k equals 1. This is a sum from m equals 0 to 1 of 1 choose m, u to the m, v to the 1 minus m. And now this only has two terms, the m equals 0 and the m equals 1 term, so we can expand those out. So this would be 1 choose 0 times u to the 0, v to the 1, plus 1 choose 1, u to the 1, v to the 0. But using a similar argument as up here, we see that anything to the 1 is just that thing prime, and anything to the 0 is by definition itself. So this 1 choose 0 is 1, so this is u times v prime, plus 1 to choose 1 is 1, so we just get 1 u prime times v. And so, well, the terms have been swapped, but these are equal. So the base case holds. Now for our inductive step, let k be greater than or equal to 1 and assume that our result holds at k, which is this big equality. U to the m, v, k minus m. All right. So that was our expression. So this is what we're assuming. Now we want to consider the k plus 1 case, which is the product uv with this operation applied k plus 1 times. Well, this was defined recursively. We know what this is. We know this is uv to the k with prime applied. And this is what we just made an assumption about. So this is the sum 0 to k choose m, u to the m, v to the k minus m, all prime. Okay. Now we have some properties of prime that we can apply. First, we know that prime distributes across sums. So we can distribute this prime across this large summation and get the following. Where this now is we're only taking the prime of the terms individually instead of the whole sum. We also know that scalars come out and k choose m is just a constant number. So we can do this. And now we're just applying prime to this product, but we also know how primes apply to products. So this is going to be um prime times v to the k minus m plus u to the m times v to the k minus m prime. By a recursive definition, if we apply prime to something like this, it just ticks up the exponent. So we can rewrite these terms as u to the m plus 1, v to the k minus m, plus u to the m, v to the k minus m plus 1. Now we can distribute this constant and this summation notation and get the following. Where we'll just have one part of this first, and then a second summation where we have the other terms, like this. In order to add these back up eventually into one term, we would like the sum ends to look the same. So we're going to mess around a bit with the indices of summation. Here, m goes from 0 to k, and it appears here as m plus 1, which means that this piece goes from 1 to k plus 1. So if we change this to say it goes from 1 to k plus 1, this part will now just be m, because this exponent went from 1 to k plus 1, and this one is doing the same. Now we just modify the other terms so that it matches. This went from 0 to k, so now we have to subtract 1 to keep it going from 0 to k. And this went from k to 0. So we've already seen we have to replace m with m minus 1. So this ends up being k minus m minus 1, which if we drop these brackets and distribute is a plus 1. So we've changed these indices. And we can leave this the same for now. And you'll notice that in doing so, we now have u to the m, v to the k minus m plus 1, and over here we have the same, u to the m, v to the k minus m plus 1, which means that we can add these where their indices match. However, this starts at m equals 1, and this starts at m equals 0. So this has an extra term, and so does this one. It has an extra term at k plus 1. So we need to pop off the last term of this and pop off the first term of this. So the first thing I'm going to do is just swap the order of these so that it makes a bit more sense. So just moving this one over here. And moving this one over here. Now, I want to take off the first term of this, which is the m equals 0 term. So that will look like k choose 0, u to the 0, v to the k minus 0 plus 1, which is just k plus 1. Since I've taken off the m equals 0 term, I can now write the rest of them, which start from m equals 1 to k. This is a k. Here, I want all of the terms from 1 to k, and I'm going to take off the k plus first term. So first I'm going to rewrite these. For now, I'm going to give myself a bit more room. And the k plus first term is where m is equal to k plus 1. So we get k choose k, u to the k plus 1, and here we just get v to the 0. All right. Now, finally, this goes from 1 to k, this goes from 1 to k, so I can add these. And since these parts here are the same, when I add them, I can just add coefficients. So we get k choose 0, u to the 0, v to the k plus 1, plus a sum from 1 to k of the exponents get added, or the coefficients get added. And the terms are these. And we have this term on the end. Now, these are binomial coefficients. So k choose m plus k choose m minus 1 is equal to k plus 1 choose m. So we can make that replacement. And over here, we'll also make some replacements. K choose 0 is equal to 1, and k plus 1 choose 0 is also equal to 1. So we can replace these. Plus, our sum is from m goes from 1 to k. This coefficient is k plus 1 choose m. And over here, by the same thing we did over here, k choose k is 1, and so is k plus 1 choose k plus 1. So this is just rewriting these coefficients 1 in different ways, but now you can see that this is the 0th term of this sum if we add it back in, and this is the k plus first term of this sum if we add it back in. So we just get the sum from m equals 0 to k plus 1. K plus 1 choose m, u to the m, v to the, I'm just going to rearrange this slightly to write it as k plus 1 minus m. And this was exactly the right-hand side at k plus 1. And so that concludes the inductive step. 4.4.3 asks us to prove this identity about the Fibonacci numbers. If we recall, we can denote the Fibonacci numbers by fm for the mth one. And these are defined recursively where the first two Fibonacci numbers are 1. And after that, the next Fibonacci number is the sum of the previous two. So this is going to be an exercise that requires strong induction, as we'll see. And so we'd like to dive into this proof. So proof by strong induction. And to note here, there's two variables. There's m's and k's involved. What we're going to do is we're just going to fix our m. So fix m greater than or equal to 2. And then we're going to induct on k. So we just fix some arbitrary m. Therefore, our argument will work for all of them. And then our base case and our inductive step, all of that, we'll be manipulating k. So k can be any natural number. So our base case is k equal to 1. At k equal to 1, then the left-hand side is just f of m plus 1, and the right-hand side is, well, this is f of m minus 1 times f of 1 plus f of m times f of 2, but f of 1 and f of 2 are both 1 by definition. So this is just f of m minus 1 plus f of m, which by the recursive definition of the Fibonacci numbers is f of m plus 1. So these two things are equal. They're both f of m plus 1. So the base case holds. Now for the inductive step, we're going to let k be greater than or equal to 1. And now we need to use strong induction. So what we're going to assume is, that for all numbers j between 1 and k, we have that f of m plus j is equal to this. So we've set our variable that we're inducting over as greater than or equal to our base case. But rather than just make the assumption for the statement at k, we're making the assumption for the statement at 1 and at 2 and at 3 all the way up to k, which is what this this j between 1 and k means. So we have all of these statements at all these different j's. Now, we would like to consider f of m plus k plus 1. We're still, just as in normal induction, consider the k plus 1 case. By the definition of the Fibonacci numbers, this is f of m plus k plus f of m plus k minus 1. And now this is where the fact that we've made all of these assumptions comes into play, because here we can use the assumption at j equals k, and here we can use the assumption at j equals k minus 1. So this is equal to Well, if j is equal to k, we get the following. And if j is replaced with k minus 1, this second term becomes this. So we get these 4 terms coming from 2 applications. This is, you can think of it as j equals k, and this application of the assumption is the version at j equals k minus 1. And we have these 2 versions because of the strong induction. From here now, we can just sort of gather some like terms. These 2 terms have an f of m minus 1 in them. So when we factor that out, we get f of k plus f of k minus 1. The other 2 terms have an f of m, and when we factor them out, we get f of k plus 1 plus f of k. These are just sums of subsequent Fibonacci numbers, which means by the recursive definition, this is f of k plus 1. And this is f of k plus 2. But this is exactly what we wanted. Since this is f of m minus 1, f of k plus 1 plus, just writing k plus 2 slightly differently, we can see that this is exactly this formula at k plus 1. That was the goal of our inductive step, so our inductive step is complete, which finishes our proof by induction.